On behalf of VMUG, I'd like to welcome you to today's webcast, Best Practices for Snapshot-Heavy Environments, presented by Tomer Hagay and Rob Girard of Tintri. Thank you for participating in today's webcast and for your continued support in the Global VMUG program. Before we begin, I have a few quick housekeeping items to go over. First, today's webcast will be recorded and available for on-demand. You'll receive a follow-up email with the on-demand link from today's webcast, so be looking out for that. Second, a Q&A session will follow today's presentation. All questions need to be entered in the question window near the bottom of your GoToWebinar screen. Third, there will be a short online evaluation that pops up as you exit the webcast. Please make sure to take a minute and let us know what you thought of today's session and what you might like to see going forward. One attendee from today's webcast will win a $100 Amazon gift card. Tintri will email the winner directly following the webcast today, so good luck. All right, let's get started. I would like to introduce you to today's presenters, Tomer Hagay, Senior Director of Product Management, and Rob Girard, Principal Technical Marketing Engineer at Tintri. Rob and Tomer, I would like to turn things over to you.
Great, thanks, Annie. So this is Rob Girard here. Been with Tintri, which is now Tintri by DDN. Been with Tintri for over 5 years, and been heavily involved in virtualization since about 2005, and have been working in IT for over 20 years now. And I'm joined with Tomer Hagay.
Hey Rob, hey everyone, thanks for joining. So I'm also with Tintri for a while, almost 4 years, and it's been almost our tradition to pick topics that are top of mind for all of us in the virtualization community, and use our sponsor session to cover them. So for this session, we chose snapshots, and we're going to talk about vSphere snapshots, array level snapshots, and of course, we're Tintri, so we'll show you some of the Tintri magic we do behind the scenes. I want to start and talk about our backstory here. So we've gone through a pretty significant infrastructure consolidation effort here at Tintri, and throughout that effort, we found that vSphere snapshots are a significant bottleneck. So we had snapshots all across the infrastructure, vSphere snapshots that have been there forever. And looking at the community, some of the forums on the VMware website and others, there's seemed to be some confusion or some missing clarity on what is the impact of snapshots. And this led me to put together this this presentation and a live demo, or actually a lab session that we'll go through later, and cover some findings from our production environment and this lab that you'll see soon. So just to start with an example and share what we're talking about. So in our production environment, we had VMs like this, right? So this is a huge VM, right? It's 17 terabyte in size, and it had a snapshot taken in 2014. So when this VM was installed, right, someone installed the OS, or it was clean OS, they took a snapshot, and then they added the entire application onto that VM, right? Everything, the database, everything ran, and essentially it ran from that snapshot.
And if I can add to that, I mean, I've seen this so many times, whether it's in my own environment, back when I was the customer side working on doing infrastructure mainly for financial firms, or here in the labs, or on the countless customers that I interact with all the time. These snapshots show up as a number of things, but a lot of times you'll see before upgrade as the name of the snap, or clean Windows install, or fresh service pack, or something like that. And it's sort of done at the beginning so that you nail it. Sometimes you even put that snapshot into your templates, and that's actually one of the worst things that you could do. But you end up with these snapshots on there one way or another, and this session is really about the impact of these.
Right. So again, there's a lot of confusion of why is this bad for you? Is it bad for you? There's some best practices from VMware talk about this, and we're going to talk about these later. So here we actually took some load generators and see what happens when you take a snapshot. But we also have all those VMs in production that we had to do something about, and in this case we had to move those VMs around, and you just can't move a 17 terabyte VM running on vSphere 5.5 with a snapshot on it, right? It's just impossible. So the first thing I did, handling this VM, I actually started deleting or consolidating the snapshot, and it took 11 days to remove the snapshot, right? So these were 11 days where, I crossed my fingers, I made sure no one touches the environment, no one touches the arrays. The arrays, the storage array behind the scenes have enough space to run this, and just make sure that the process completes, because this was a really, very important mission critical VM. And as Rob mentioned, right, we see this with customers all the time. In some cases, I'm sure you all on the call kind of chuckled when you saw this, this VM with a snapshot. And I know that this is a struggle for many of you, right? Sometimes your users want to have those snapshots. Sometimes you have to use them, and you can't delete them because there's a need in your organization and everything. So this session is really about to arm you, if you're not familiar with that topic, with the information that you need in order to make those decisions. So we're not going to make any recommendations, right? I mean, snapshots are good for some things, maybe are less good for other things. We'll show you the facts, and then you can decide.
So I'm a huge fan of snapshots, and I believe in them heavily, and I want to use them heavily. It's so much easier and quicker to roll things back,
right,
if I need to, right? This is the benefits of virtualization we didn't have in the physical world. And so, keeping that in mind, we're not saying there's not ways to snapshot. We will cover ways you can snapshot, but this is really the, hey, just know which tools you're using and the impact of them, and let's get into detail more.
Exactly. So looking at, what is a snapshot, right? I mean, I assume all of us on the call know what they are. This is really just to set the stage. So what a snapshot is a file-based representation of a state, right, of a virtual machine in a given time. And in snapshots or with snapshots, there are different consistencies. Rob, you want to tell us a little bit about the differences?
Sure. I mean, so crash consistency would be if you took the classic old school server where all the storage was directly attached, and you didn't have battery backed or array cards and stuff in it, HBAs and stuff, and then you just pulled the power and all of it went down clean, right? So and then if you're looking at it from a sort of a disk perspective, this is just stop the disk at a certain point in time, no more writes to it, which in a virtualized environment where your storage is often separate from the actual compute and stuff, this is that point in time, and it's up to the operating system and the applications inside to know how to recover. And some applications, SQL Server in particular, do an amazing job at recovering from crash consistent, assuming all the disks are snapped and are crash consistent at the exact moment in time. Now, application consistent is where we give the operating system and the applications a heads up. So on a Windows environment, this typically involves VSS, the volume shadow services, and it will quiesce things inside. If you're in VMware and you make a snapshot and there's a little checkbox that says quiesce disk, that says, oh, okay, tell the application to settle its IO, to flush all the any of the dirty pages that are in memory down to disk, and then it writes little signatures in the applications that says this is the clean break, so that when it comes back up, it says, oh, I found a spot that's clean. I'll just throw out all the junk that accumulated right after that and go from my nice clean break. Now, in terms of crash consistent versus app consistent, that is not the focus of this session. This is about the physical effects of the IO of having a snapshot. For more information on this one, I've done a VMworld session for a number of years, presented on VMUG as well. You can ping us for that URL or just search for it. That one was snapshots in a SQL environment, and it's about an hour of deep dive into the difference between these two.
So obviously this is a very high level overview, right? Like you said, Rob. So we have that session on you can find it on the content library on the VMworld session.
And so for the sake of this demo, we're going to do the crash consistent. So the crash consistent is the no impact to your guest, no quiescing. So we're just going to see when you just hit it and all of a sudden we create a snapshot in a new Delta file, and we'll cover what the mechanics are. But we're not telling the guest to do anything different. We're not informing it that we're doing these things,
Right.
and we're going to observe the performance behavior of it.
Exactly. So, and then for just to complete that definition, you know, we gather two types of snapshots here. So, storage array managed or hypervisor managed. The vSphere snapshots we're going to talk about are hypervisor managed, and then we're going to talk about storage array snapshots. So, looking at the best practices from VMware, right? So, you know, we want to use snapshots, right? Then we look to VMware to tell us, you know, what's recommended, right? So this is kind of a summary from one of the articles, right? And this is relevant to all the versions, right? So you can't say it's like old or whatever, right? This is to all ESX versions, right? So what do VMware tell us, right? So first they tell us don't use snapshots as backups, right? Because these are, again, file representations in the same storage location, right? They're probably not as good as, you know, full backups in a different storage location.
Yeah, from a disaster recovery perspective, something goes wrong on the storage. If something goes wrong in the file system of where that base snap is, and these snapshots rely on reading those base bits, then it's going to be just as corrupt inside your snapshots as well.
Right.
So you know, make sure that when you're protecting yourself, you've got another copy of the data that's on a different device. Whether that's through replication, backups, there's a lot of ways you can do that.
Right. So then we move to the two other bullet points here, which are quite confusing, right? So, you know, the VMware tells us that we can use a maximum of 32 snapshots, right, that are supported, but, you know, don't use more than 2 or 3. Where, what does it mean, right? Is 2 okay, right? How long can I keep them, right? So, you know, again, VMware tells us, you know, it's not recommended to keep those for more than 72 hours. But again, what does it mean, right? If I have a VM that's very heavy and, you know, writes a lot of changes all the time and everything, you know, can I leave it there for 72 hours or an hour? What is the performance implication? What are the, you know, the storage implications? So these are obviously some guidelines, but, you know, your mileage may vary a lot, and then it doesn't talk about what you're actually missing when, or what you're going to lose when you use those, you know, even 2 or 3 snapshots.
And before we move on, we've got a question here from Carlo, and it's a great question. It says, you know, last I checked, Oracle and Postgres both support recovery using crash consistent snaps, but Microsoft does not support crash consistent snapshots. I agree with your statement that MS SQL does recover well from crash consistent, but any idea why Microsoft states that they don't support this? Yes. So from a Microsoft perspective, they don't know where you're snapshotting. They don't know the mechanisms of it. And for an application like SQL in particular, if you're following best practices and you have your data and logs on separate drives, it is incredibly important that your snapshot is taken with like a true point in time, a true crash consistent, like you pulled the plug. And a lot of times you'll end up with caching, you'll end up with queuing, and the queues to the different LUNs where you might be storing these different files or to the different disks might be in different states. And if your LSNs, your log sequence numbers, are out of whack between your between that data file and the log file, you can get a lot of issues. And so there's a lot of people that have seen crash consistency not working very well. And I want to point out that on a Tintri perspective, all of these exist in the same place. If we're doing a snap, it's the exact same point in time, and it affects all the disks at the same time. That can't be said for other things unless application groups are done. And most of the time, even with those groups for multiple LUNs together, you need to do some quiescing on it because there's other queues that prevent that write order preservation and prevent your bits from actually being written to disk in the sequence they're supposed to.
Right, so we haven't talked about array level snapshots yet, but that's where, you know, in various arrays, you have to go into consistency groups and other types of mechanisms to try and have all your queues grouped together in one group. On a Tintri array, we use the VM itself as the group. So when you snap a VM on a Tintri, right, by definition, it's all the order is preserved and everything is in the same queue. But like we said, we have a whole session on that.
Yeah,
right?
if you're interested in SQL, I mean,
Yeah.
that dives in very deep.
Yeah.
I don't want to kill the time on this one.
Yeah, Thanks, Rob. So anyway, with that in mind, right, with all this, and that's, I think, one of the reasons why, again, in forum and in some user conversations I had and everything, there's a lot of confusion. Okay, yeah, I keep one snapshot. It's not too bad. VMware says, 2 or 3 are fine. So I'm with one snapshot. So, okay, so let's look deeper into that. Looking at the snapshot hierarchy in vSphere, and this is a diagram that you might have seen before. I mean, it's there in a lot of the papers from VMware and from others. And it starts with, when you take a snapshot, what happens is that the hypervisor creates a delta file, right? So you have your VMDK that used to be a flat file. All the writes were written into that flat file in a very simple manner, right? So it just mimics a big volume behavior and writes to blocks, quote unquote, in that file with an offset, right? So that flat file is very efficient. But when you add a snapshot, a delta file is created, and that delta file has to include something like a mini file system, right? It has to understand where blocks reside, because now you have some blocks or some data in the delta file and some data still resides on the original flat file. So then that process takes place every time you add another snapshot. So the more snapshots you have, that hierarchy becomes more complex.
Okay. So I always found this diagram to be confusing.
Yeah.
So you got a better one for us?
So thanks, Rob. So what I did here, I actually borrowed some of Rob's slides and from the SQL session and created a much simplified version of that, right? So just again to be all on the same page. So let's say we just created a VM, right? It has an empty vdisk, and this gray area represents all the blocks in the flat file, or all the space in the flat file. So all the space is available for us to write data in.
And to help you visualize this, just pretend that every pixel on your screen is a block on the file system. Okay, so right now, gray has not been written to, it's empty. The start of the disk is at the bottom, so we're gonna fill it up, and let's write some data to it.
Yeah, so then we took our empty VM and we installed an OS on it, right? So now we have this available space on top and then the OS at the bottom, right? Because we started writing into the flat file. And then we said, oh, awesome, right? We have a clean VM with a clean OS. We're gonna take a snapshot, right? So we took a snapshot of that VM at that point in time. And then we installed an application on top. So the application takes more space, and then we still have an available space on top. Now, as part of this application installation, we also touched some of the OS blocks, right? Let's say, we wrote some logs and, we added users. So now we have information that spans across, the application and the OS. So if we look at what we have in each one of those files that we talked about, right? On the flat file, we have the OS, right? That's the flat file content. But since we took a snapshot, we also have a delta file. And the delta file contains the application and the users and the logs, which change some of the blocks on the original OS flat file, right? So something has to manage that mechanism, right? That copy on write to be able to preserve the old state, but also change that and override, quote unquote, some of the blocks that were originally there in the flat file. So Rob, do we have any questions? I think we have something before we go to
not related
the lab here. So with that in mind, let's move to the lab and see see how things behave in a live system. And what's interesting about this live system is that we use the Tintri arrays in the back end, right? And the Tintri arrays can show us a very detailed view of the IOPS, the latency for each one of the VMs that we're going to work on, right? So for this session, I prepared a few VMs, just called them low-gen, and this one is read-only, read-write, and write-only. So I just clicked this read-write VM, and you can see that we can see the IOPS in real time for this VM. So we're at around 2,600 IOPS with 2,000 IOPS on reads and around 520 IOPS on write, right? So we can see the blue and yellow areas here. On this VM, this is a write only, so we can see blue, and we have slightly more IOPS there, right? So 3,500. And those VMs reside here on this vCenter, right? So we have those 3 VMs here. Okay, so what is this workload that we're running? So this is a very simple load generator that we've created here. It's a program written in C++, which allows us to generate IOPS with different compression ratios and dedupe capabilities. And we can see the same number of IOPS here. So I don't know if you can see in the middle of the screen here, there's where it says IOPS, right? There's around the same numbers. So this is the write only, shows around 3,600 IOPS. And if we look at the read write, we'll see the same numbers, 2,600. And this is important, right? I'm mentioning those numbers because now we can see that the array reflects the same amount of IOPS as the VM, right? So the VM gets its 2,600 IOPS and the array serves 2,600 IOPS, right? So they're in sync. And in this case, all the data that this VM writes goes to the flat file. All the data the VM reads comes from the flat file. So if I look at our ESX for a moment here, right, we can see the files. So we have these 2 flat files. One of them is 2 gig in size, which is the OS, and the other one is 50 gig in size where we generate the data. Okay, so what I want to do now is take snapshots. So we have our read-write VM. We're going to take a snapshot. So snapshot, take a snapshot. I'm going to remove that. And then the write only, we're going to take a snapshot. And we're going to do the same here, right? So we have those 2 VMs. We took snapshots on both of those VMs. What I'm going to do is just hit refresh on this one, and it will refresh the data. So out of the gate, I wanted to look at the IOPS and what we have in the IOPS now, right? So this read-write workload went down to 1,500 IOPS, right? The write-only went down to around 1,000 IOPS, right? So we have a significant drop in IOPS, right? And this is, well, I guess I can explain a little bit about the workload itself, right? So we're actually allocating one CPU thread to generate those IOPS. Now, if the CPU thread is, can easily generate those IOPS, then, you'll see more, right? If it has latency or it's busy with doing other things, other operations, then we'll see less IOPS. So we saw this drop in IOPS, and I want to explain why that is.
And another comment on this tool, this is an internally written Tintri tool. We call it Tingle. It's available on our support portal just to run. But essentially, it's not really realistic because it's like heavily feedback sensitive. So it won't issue the next IO until it gets one. And when we say that there's only one thread going on,
right,
that IO goes, we wait for a response before we send another. And then we also list out there the milliseconds average and max, and you can see those are 0.75 on average, and that's the end-to-end travel for any given IO. And the max is for one of those IOs that are happening inside of that second.
Right, so for this exercise, this workload is perfect because it shows you a real view. So if you pay, quote unquote, more for every IOPS, then you'll have less of them, right? And that's exactly the point I wanted to show you here when it comes to performance impact when you use a snapshot. So let's go back to our VMs and see what we have here. So now we can see that this workload has reads only, right? So Rob, can you tell us where are the writes?
Well, they don't appear to be here. So we are writing into a new snapshot. So we're not writing to our base disk, right?
Correct. So we have a Delta file now in place. So let me go back to our presentation here for a moment and show you this diagram again. So now what we have is this situation here, right? So we have the flat file, but the flat file is now untouched, right? And then we have the Delta file on top, and the Delta file on top is the one that receives on the all the writes. So the Tintri array looks at the reads and writes coming in, and it maps them to files. So in our case, what we do is we sync with vCenter every few minutes to know which VMs own which files. And we just got a new file, which is the Delta file for these VMs, and therefore that IO view is not accurate at this point. So it will take a couple of minutes for it to sync up and understand that there's a Delta file and show us the new state. So in the meantime, what I wanted to do is explain a little bit about what's happening inside the Delta file, right? So this is very important for our understanding of the performance implications, right? So we talked about the flat file, right, which is very simple. You just write to it. There's an offset, right? It's very efficient. Whereas when you have a Delta file, I mentioned earlier, it's like a mini file system. So what you have in that Delta file, or what the hypervisor maintains in the Delta file, it maintains a list of tables and directories and blocks, right, which are called grains, in order to map which data resides where. So as soon as you took the first snapshot, the ESXi host has to write the state or the location of each block somewhere, right? And it writes that in the header of the first or the latest Delta file. So and that's why I wanted to show you the structure of the Delta file. So whereas many of you are probably familiar with the diagram on the right, on the left, the one on the right is not very I don't know.
It's not very well known.
Yeah, well known, I guess.
Yeah.
Is the right.
You really got to be digging deep to be getting into this level.
Right. So that's just to show that this Delta file is very different, right? It has those multiple grain directories, and then inside there are grain tables, multiple grain tables, and those grain tables point to grains. So because this is a Delta versus flat, right? The VMware calls it grains versus blocks, and all those are maintained. So for every read and write that the ESXi host performs, it needs to go to those grain directories and grain tables to understand where to find the data or where to put the data, right? And that's where we have this single thread that we have right now in that workload works harder for every IO compared to the work it had to put earlier. So let's go back to our lab and see where we are with that. So maybe I'll just open this here. And maybe it will take us another minute to refresh.
Yeah, not showing yet.
Not showing
and
yet.
Again, just to reiterate, this is a Tintri UI thing where we've got to map the files together with to associate it. So when we're looking at a VM, and we're looking at this VM here, it's a combination of all the vDisks on it, and we've added these this Delta as an extra vDisk that is being read to, and our UI right now is only responding to that base one. But rest assured, when we show inside the application, those IOs are true from an application perspective. It knows what it's writing down. And this small delay can be a few minutes. The data really is being written to that Delta. It's just taking us, our UI a little bit to sort of true up. If you were looking at anything historically, you wouldn't notice any of these gaps. We're looking at it real time at 10-second averages. All of our historical data going up to 1 week or 30 days inside of Tintri Global Center would be at 10-minute average granularity.
Right. So in this case, this proves that writes go somewhere else, right? Reads still come from the original flat file, But as we write more data, more of those reads will come from the Delta file, right? Because we change more blocks, quote unquote, on this VM. So we'll go back to that. But what I wanted to do later is just to look at the numbers before and after, right? So we've talked about much higher numbers on the IOPS on both VMs, right? We had around 3,500 and 2,500, and that's where the IOPS here really dropped. Now, once the array will refresh itself,
and we just hit a 10-minute chunk, so I think that we should see it.
Okay, good, yeah. So this will come up really soon. But what we'll be able to see is that the array still gets a lot of those IOPS, right, are generated because that single thread still works to read and write data to and from the disk. But now it has to work much harder, right? So all this work goes into IOPS that the array sees, but those array IOPS are not visible to the VM, or the VM cannot benefit from those IOPS.
And staying in this view, one of the things that is really subtle, and I'm not sure if you can pick out or not, perfect. We're just getting our update to show it accurately now, is that right at the beginning of the graph here, we can see that we're, so from here, it is just the one vDisk. Then we put a snapshot on, so there's a delta and a base vDisk. And then as we go here, now we're showing the combination of both of them. So the aggregate of the delta and the base. Back here, what we see is that the IO that is being read from that base disk is slowly decreasing. Yes. And the reason is that as we write more data, and again, we're writing at about 500 IOs per second. And as we write them into the delta in the snapshot, if those exist in the delta, then we can read off it, and we don't have to miss the delta and then read the base. So the amount we need to read from the base starts to decrease.
Exactly. So the base becomes obsolete as you overwrite, quote unquote, or you change the blocks that were originally stored in the flat file. You store them in the delta file. So the delta file serves the data instead of the host hitting the delta file and then go to the flat file to fetch the data. So what I wanted to show here, right, which is really the important point of this, one of the most important points of this session, right? So if you dozed off a little bit, now is the really important time to look. Now we can see that the array still sees 2,600 IOPS, around 2,600 IOPS here, right? This is you see the total there. And if I'll go to the same VM, right? And what I can see from the VM level is that the VM sees 1,100 IOPS. So that means that we generate over 2x the amount of IOPS at the array level, right? So the array has to serve over 2x of the IOPS just for every IOP that the VM actually uses, reads or writes, right? So there's a huge overhead to this, and that overhead varies based on the workload, right? Based on the block size, based on the read-write ratios, and several other factors.
And there's one more layer of overhead that we're not showing on the Tintri side, because we've got a custom proprietary file system that we wrote from the ground up for virtualization, and it presents itself as NFS. If this were block storage with a LUN and we had a data store on it and installed VMFS as the file system on it, the LUN would not only see all of this, but the LUN would also see some calls from the hypervisor hosts that are metadata associated with the VMFS. So there's even more overhead of some writes associated with it and reads associated with it that have nothing to do with the payload inside your applications.
Right. So that's where, I actually wanted to show you a few things before we dive deeper into this. And that thing is our write-only workload. So the write-only workload now sees around 1,000 IOPS. If I look at the Tintri array, right, what the storage array sees for that VM, right, you can see that suddenly we have reads and writes. So how come we have reads for a write-only VM, right? So earlier it only had writes, which is the write state, right? Too many writes here, but in the sentence, but
right?
Exactly. So Now we can see that for this workload, this is a write-only VM that generates read. Why does it generate reads? Right, so the ESXi host, again, has to go to those grain tables and grain directories and grains and read all of that data for every IO it serves, right? So that's where you know, even though we're just writing, we can see that we're actually reading a lot of data. So so we're reading half the amount of data, right? So 970, right, out of 1800, right? So we're reading, you know, we're generating a lot of IOPS.
So a lot of overhead. And so my belief in the past was when I'm looking at, you know, I've been using Tintri VM stores for over actually over 7 years now. First as a customer for almost 2 years. And what I see here, you know, I was believing that, hey, my workload, just that's how much data is being written. That's how much IO is going. And I know because it's per VM. And so some of these findings that Tomer's been working on and we've been, you know, doing in the lab was really eye-opening that just how much overhead there is. So if you've come from a networking background, just think of adding frame headers or encapsulation, right? All the overhead that's associated with that. Or if you come from a storage background, what we're talking about are really blocks and extents. And there's a bunch of blocks together in an extent. And in order to modify that extent, we got to read some of these blocks out, read a previous extent, and then reread the existing data, and then just rewrite that extent with just the blocks that have been altered, but the whole extent has to. And the same kind of applies on VMDKs. If you notice that the rate at which it unthins, I'm not sure what it is nowadays, but if you look on VMFS, even when it was thin, it would show up as 16 megs. And every time you had to write out a new portion to write to, it was always 16 megabyte increments as those increments were, those extents were laid down.
Yeah, so my personal belief when I worked on this for years, right, on VMs with snapshots and everything, I believe that, and I think that's common across, I heard many people talk about this way, that writes go to the delta file, right, so that you won't have an impact on writes, right? You'll only have impacts on reads because if you miss the delta file, you have to go to the next delta or to, you know, the parent flat file, right? So you'll have an impact on reads.
And we can see in reality that a purely write workload is requiring reads.
Exactly. So that is an eye-opening, you know, experience for me, I guess, in this. And this is, you know, this led me to write this summary. And I heard from a colleague this term around goodput and throughput, right? So the fact that you have throughput doesn't mean that you have goodput, right? So the VM sees 1,000 IOPS, the array sees 3,000, right? The storage guy might say, hey, you know, yeah, I'm serving all these IOPS, everyone's happy, but the VM actually gets 1/3 of that, or 1/2, or 1/4, depending on, you know, the block size and again the latency and other parameters in the stack. Again, to me, an eye-opening experience was that write operations are impacted as well. Not a lot of people knew that, including myself now. Now it's obviously clear. And like I mentioned, block size would change some of those ratios that we saw.
Now, we didn't cover block size, but if you could just go back to the demo for a sec, I'll show you something that's kind of specific to Tintri. That checkbox in the top right corner for QoS, this tells us the normalized IOPS. So our file system is an 8K file system, and anything that's up to 8K will show as one IOP, is, you know, one IO is one IO. Now, if the block size happened to be 16K, right, and there's one IO of 16K coming in, that's still one IO, but you're putting a lot more through it. Or if you have a large block workload of 256K, that's still one IO, but the data payload inside of that is 32 times larger than an 8K. So what we're showing with this normalized is sort of that amplification. So if this was apples to apples, looking at as if they were all 8K, and you can see to the left, there was no overhead. So our workload is an 8K workload, and these operations that that have to be done from vSphere to interoperate with those deltas and to access those grain tables are not granular small 8K. They're coming in larger, and they're doing that so they can kind of grab stuff as a sweep or accumulate quite several of the IOs together and then write them down in a larger block size. So now from a storage perspective, if we tuned this for an 8K workload, and now we've put on a VMware level snapshot, we've it's not an 8K workload anymore. So if we've optimized for an 8K workload on the storage side, if your storage allows you to tune that kind of stuff, and you know, we fundamentally just changed the workload. And so we've seen kind of penalties across the board. We see that this is not all good put. This is like a lot of overhead going on. And we're only looking at one VM. So you imagine that you've got tens, hundreds, thousands of VMs, and they're all mixed inside of a LUN in a data store. If you don't see the granularity underneath, you know, there's a big mix that's going on at the array level. And there's no way to say who's getting what, how much they're doing. And if you were to reconcile from inside your applications to what's actually being processed, and then check your storage, you're going to find this gap and this delta. And I think that on the Tintri side, we're going to have the delta as narrow as possible. We've gotten rid of all the noise except for what is specific to these VMs, and we still see that there's this delta here.
Yeah, good points, Rob. Thanks. So I guess bottom line is that earlier we had an 8K block size workload with read only. After we took a snapshot, we have different block sizes and we have reads as well, right? That just show that. So going back to our slide here, one moment. Yeah, so we talked about the good put and throughput and everything. We're good on this. Now let's go back to removing snapshots, right? So, you know, in a snapshot heavy environment or in any environment, you know, you put snapshots on, and, you know, maybe after the session, you want to remove some of those snapshots. So you know that are, you know, even worse for you than you thought. This example, right? This is the production VM we talked about earlier, you know, with the 11 days to delete the snapshot. So what actually happens when you delete the snapshot? So again, there's a lot of confusion in the community around that. Do I need more space when I delete a snapshot, right? Well, I need more space on the array or not, right? So I captured some screenshots while those snapshots were deleted, or while that snapshot on the big VM was deleted. And what I saw is that, and this is a screenshot from the same view that we saw before on the live system. This is taken at the vDisk level. Right, so we can see that per vDisk, ESXi goes, you know, vDisk by vDisk and consolidates the Delta file with the flat file. So you can see it ran for 2 days here to consolidate this one vDisk, and then went to the next one, ran for 2 days, went to the next one, ran for 2 days.
So this actually may have had writes and reads to it earlier, before what we can see in this 7-day view. Right. And then because the process is taking so long, we got to come back and start truing up our vDisk. So even we go vDisk to vDisk. Let's say that we did this vDisk first early on. It's got these 003. If we went through them sequentially, we know that there's at least another one that's 013 on there. So we go through and we do this one. Later on, we're going to have to take the snapshot on that's there during the process, and we're going to have to merge that back in. So we got to always make sure that we're doing this. Now, what you're seeing on the left of the divider is you're seeing space, and it's no coincidence that the space is 2,000 gigs. So if you look to the right of it, 2,000 gigs is that disk without any hypervisor snapshots on it. Right.
That's after the deletion, right? You said
after the deletion.
The IOPS ended, and then that.
Yeah. And this is the point in time from that event log that Tomer had screenshotted that said it was complete. The whole operation complete 11 days later. Now, if you ignore the green portion on the right and you just look at the base disk, this disk is and up in the top you can see it's provisioned at 2 gigabytes.
2 terabytes.
2 terabytes. Sorry, 1,900 gigabytes. And so what we have on the left side is that disk itself, and then since the snapshot was on more or less since the inception of this VM, we had data in there. We then had this, pretty much every block in there had changed since then.
Right.
And so then we had another copy in the delta. And then that third amount, if you're wondering where that came from, that one is coming from the new VMDK that's being written down that has to accommodate the merge operation that's happening. So we got to keep our delta and our base together, and leave them alone. That base is in a read-only fashion. It has to stay that way while we do our deletion, which is like a merge, right? We're putting them together. We're writing to a new VMDK. And so you could need up to the full amount of the vDisk, or all the sum of all the vDisks for a VM, depending on how much was changed, in order to go through this delete snapshot view. Now, fortunately, you only need the amount of, potentially 2x all the vDisks. In the past in vSphere, and I've been bit by this, if you had a snap chain, you would need to have enough space for every single one of those to write a new VMDK.
Correct.
Clean again, and again. So if you had 4 snapshots on there, potentially you would need 5x the space. And until the entire operation was completed, you don't get that back. And depending on your disk subsystem, even once you delete them, those blocks are dirtied, and you may or may not get them back from an array perspective. So from a Tintri's perspective, you delete a vDisk, you get that space back. We reallocate it. On a LUN perspective, you will rewrite to it, but the space that the LUN is taking will be a high watermark. And the only way to get that back is through SCSI unmap command. So there are unmap commands to get that back. Typically, they require some zeroing out. Some arrays might do it automatically as a post-process or on a weekend thing, and eventually give you that space back. But there's lots of impacts to this.
Right. Yeah. So Rob, we covered many areas, right? And of course, all the SCSI and the zeroing operation, everything. These are not relevant to what we do in Tintri, right? On the Tintri side, you don't have to worry about it, and that's really what I showed here, right? So I just triggered this snapshot removal operation. You can see that we generated a lot of IOPS to consolidate those delta files and flat files, and then we went back to the original workload.
So one thing to point out in the top portion of the graph with the VM that we're seeing, it's no longer bold. So if it's bold, that is a Tintri thing that says, hey, you have a VMware level snap, and we've got the ability to add a space field here. So I'm going to just add a field here for a hypervisor snapshot right here. And we can see that since we started this test with the read-only, we had 3.2 gigs that were written that were exclusively for the snapshot. And the one above that says 0.9, on the next refresh, that will end up becoming 0 again.
This updates every 10 minutes. So essentially, this 3.2 is probably higher because this has refreshed a few minutes ago.
So for Tintri customers, if you're on the hunt for snapshots, add this field to your VM list, right? And when you don't have the filter for VMs and you see your hundreds, thousands of VMs, add that field, sort by that. Anything that shows up, that's where you're going to go hunt down and get rid of these. And we never covered latency on this. I should have pointed out while it was there in the real time, but we had some latency that was showing up with our snapshots, and we were seeing some host latency associated with it. But yeah, that's okay.
Yeah, that's probably for the next session. So we can move forward. So obviously we saw this IOPS spike as we were removing the snapshot. And we talked about the implications on that. But what I want to show you, back to the slide and back to this huge VM, right, that ran for days, right? That snapshot consolidation ran for days. One of the reasons why it ran for days, it was because it was on a hybrid array, and we got a lot of latency because the VM or the ESXi host had to read a lot of cold data from disk. So if you have disk-backed storage, then you'll have that latency when you have that consolidation. Now, I wanted to touch on, the snapshot removal, the good news, right, for what Rob was mentioning. So since ESX4 update 2, right? Every modern release of ESX essentially is able to consolidate those 2 files, right, the flat and delta file, without consuming more space on disk, right? So one might argue that this makes the process slower, right? Because now you can't generate a 3rd file, you have to consolidate within the same space and everything, but that's really good for, you know, your space consumption while this consolidation takes place. Now, one thing you have to really be careful about is array level snapshots. So if you have a snapshot schedule on the array level, or your storage guy set a snapshot schedule at the LUN where this VM resides in, that VM is going to have huge delta, right? Huge amount of changes coming in, right, while the snapshot is consolidating. So the array will see the higher change rate, and every array level snapshot will consume more space. So in my case, I had to manage the array and to make sure that the array won't run out of space as I was snapshotting this VM with array level snapshots that now took more space, right? And this is a really important point when you're doing this massive snapshot removal, if you do that. So this is another look at the long term, and this is the point that I wanted to make here, right? So you can see that the data, right, the size of the data, that's the blue here, that drops significantly, but the Tintri snapshots, the array level snapshots, go up. And on the Tintri snapshots, and we haven't talked about those, but these are, you know, really, that's a really powerful tool, allows you to snapshot at the VM level, not at the LUN or volume level, without any of the performance or space implications we saw earlier. But for this graph, right, so those Tintri snapshots were running in the background all the time, and you can see that they started to consume more space as the change rate for the VM was much higher while we deleted the VM level snapshot, the VMware level snapshot. So this is really what I wanted to cover for this session. So we talked about the performance implications. We talked about a little bit about the space implications. You know, you can see that if you took, in our case, we took a snapshot really early, you know, at the VM, this specific VM in our example, right? So then we actually doubled the space. In other cases, of course, you know, like I mentioned, your mileage may vary, but there's, you know, it's nothing new that snapshots take more space.
So why don't we, we're getting close on time. We've got about 8 minutes left. Why don't we cover all the cases where people are using snapshots and they didn't know it?
Yeah, so we can definitely do that.
Go back one.
1 second. Okay, yeah. So
yeah, so if you are using a linked clone, then you are using snapshots. You are using the same file structure. You're using hypervisor level snaps. So if you're using Horizon View for your VDI, there are different ways to deploy your pool. And if you go with a linked clone or instant clone method, you are using VMware snapshots underneath. And you have a base disk. The only difference here is that that base disk is being read by many VMs instead of just one. So that base disk has to stay read-only. vSphere takes care of that for you. And as you mount that base disk into another VM, that VM is essentially set to independent non-persistent. So it has a delta and doesn't keep any of the data on a power cycle. So it will on a reboot, but not on a power cycle. And that will keep that base disk locked. So it's a great technique to save on space because you only need the amount of one base disk and then the delta of every VM accumulates. However, there's performance implications. Citrix MCS, the machine creation services, will also operate using linked clones. And on Horizon View, there's an option called VCAI, which is, I think it's vCenter Array integration. The C is something else. It's composed. VMware Composer Array Integration, or anyway, it is leveraging VAAI, and the VAAI says offload your snapshotting down to your array level if that supports it. So and you're cloning. So if your array can support that and do the cloning, then you're good to go.
Yeah, so Rob, you touched on a point that we haven't said specifically, right? So linked clone use the exact same snapshot mechanism, right? So that delta and the grain tables and everything we talked about, right, are there for a linked clone. So every application that you have, every infrastructure level application that uses a linked clone or linked clones, right, for just to generate more copies, whether it's vCloud Director or others, right, will suffer from the same performance impact and the same space implications. So with that, I think we have.
So yeah, I've got a question here from Craig. Great question. It says, have you ever let a Tintri snapshot stay around for multiple years to see how it takes to clean up like you did with VMware? If so, was the consolidation time faster of the Tintri snapshot? Awesome question. Yeah. This was not seeded by us, but I wish I'd thought of the question because it plays right into some of our strengths. So Tintri uses a proprietary file system and multiple log mechanisms inside so that snapshots do not have a performance impact to them. And I would say that the same is going to be true for enterprise grade arrays. They have enterprise grade snapshots, and their snapshots are not going to have won't necessarily have a performance implication. Right. So in the case of a Tintri snapshot, yes, not only have I seen them around for a long time, here in the lab, I've got ones that are over 5 years old that I'm routinely running into that are manual snapshots. So if you're doing a snapshot schedule, you have a retention period and they expire afterwards. And when they expire, there's no performance hit to do that at all. And when you manually delete it or it expires automatically, all of that extra space that comes from that snapshot is going to be, the pointers are going to be pointed to a new place. And then that space, once it's just plain freed up, that's reclaimed as part of our normal garbage collection.
Right. So at that point, I wanted to clarify, right? Because I think the question really brings up the different mechanisms that are used at the array level snapshots and vSphere snapshots. So vSphere, on the vSphere side, the ESXi host has to maintain that table that tells it which block resides where or which grain resides where. A modern storage array does that natively for all the data that comes in. So on a Tintri array, we maintain this metadata that tells us where are the blocks for each VM. And in this case, I just took a snapshot of that VM, and you can see that there's no performance impact. And if I look at view snapshots for the array, for the VM, sorry, you can see that this loggen read-write has a snapshot that I just created. And there was no hit on performance, of course, because this is an array level snapshot. All we did is we had some metadata operations to say, this snapshot is represented by this set of blocks, and we start writing more blocks as data comes in. So as I delete the snapshot, and in a Tintri snapshot chain, you can delete any snapshot you want in any order, right? There's no meaning for the order. You can just take a snapshot in the middle and delete that.
And if there are dependencies on that snap because you've cloned it or something like that, we've got all the safeguards in place that if it would harm you, we won't let it. So you can try and delete any ones you want, and you'll end up clearing up some space from that, and you'll end up losing your granularity to rollback.
Yeah. So I just deleted a snapshot. You can see there's really no difference in the IOPS, right? It's the VM still has the same amount of IOPS, right? It's back to this 2600. We had it before, we had it after, right? There's really the VM, the ESXi host doesn't know that anything happened and just operates normally. Everything is handled in metadata pointers and not in blocks and other tables.
So we're just out of time. There's one last question. I'll try and answer quickly. It said, can you delete a snap while doing a migration? I'm not sure if you're referring to a Tintri offloaded migration or a vSphere storage vMotion. Storage vMotion, no, it's going to lock it down and not allow it. On a Tintri side of things, If you are deleting your vCenter snapshot, if there happened to be one on there, we take all of that into account. That's not going to be a problem. There is a portion of the offloaded one that the vSphere actually sees that it's doing a storage vMotion migration, and it will prevent you from deleting it. As far as deleting Tintri snaps while this is going, that won't be an issue. In fact, they do happen if they're aging out and expiring. So both file systems where the snaps reside, we replicate all the snaps in advance. If you happen to delete one of those snaps ahead of time, we will account for that on both sides, and the snap mechanism will roll the data up. So good question.
Yeah, thank you. So with that, I think we're at the top of the hour, and we covered a lot. So hopefully this was very beneficial and some maybe eye-opening in some cases. So really appreciate you guys joining, you all joining, girls, guys, and thanks for the questions. Annie, back to you.
Great. Well, thank you so much, Tomer and Rob, for taking the time to speak to us today. One attendee from today's webcast will win a $100 Amazon gift card, and Tintri will email the winner directly following up the webcast today. So good luck. And as a reminder, you'll receive a follow-up email with the on-demand link from today's webcast. And to find out more about the VMUG webcast program, you can visit vmug.com/learn. And please make sure to complete the short online evaluation that will pop up as you exit the webcast, and let us know how you thought today's session went. And from all of us here at VMUG, thank you and have a great rest of your day.